Okay, so as Peter was referring to, we had this epic piece of work which started almost a decade ago and culminated in what is now known as the LDBC S&B Business Intelligence Workload. To give you a bit of a context, I have drawn this imaginary data pipeline where you have your transactional data system with your daily transactions. This can be a MySQL system, it can be Postgres, Oracle, or something similar. And it's quite common to take a dump of this database, clean it, aggregate it, and then have a static snapshot of your data. And this is then subject to various systems which analyze them. It can be machine learning, it can be graph analytics, or it can be something like a data warehouse where it gets heavy analytical queries. Of course, if it's data warehouse, it's desirable to have periodic refreshes. One way to do this is to hook on the transaction log of the transactional system with technologies like Oracle Golden Gate or the Bezium. Also clean and aggregate the results of that, and then turn it into some sort of trickle updates. How often these updates arrive is often just a parameter of your system. It can be a daily update, especially in traditional data warehousing, or it can be a continuous stream of updates. So if you think in LDBC terms, if you have graphs in your transactional system, then the S&B interactive workload is the one that's representative of your workload. If you have graphs in your static analytical system, we got you covered with the LDBC Graphalytics Benchmark, which works on untyped static graphs and runs algorithms like BFS, PageRank, shortest path, connected components, and so on. And now we wanted to cover the second analytical system, the one that does heavy hitting queries, but has updates as well. So we designed the S&B BI workload. In short, the S&B BI workload is a modern all-up benchmark suite, primarily targeting database systems, but also data analytical systems. It works on a correlated temporal graph dataset. It has analytical queries, which also include graph operations like pathfinding. It has refresh operations in the form of inserts and deep deletes. And it has a unique parameter curation technique to ensure stable and predictable query runtimes. Let's take a look at the dataset through an example. So what you can see here is an actual graph instance, with the core being the social network of people. So these are people who know each other and tend to do activities together. And in the social network, they communicate through forums. Forums are just one layer between the persons, and all the forums have trees of messages, which start with a post, and then comments are sent as replies. And the graph is very heavily correlated both on the structure and on the attribute level. So here in this group of friends, we have people who live in France and they tend to have French names. But also there is correlation on the attribute level because these people are likely friends because they attended the same university. So there are correlations on both the attribute level and both on the structure level of the graph, which makes quite a few queries more interesting. The graph is dynamic, so there are timestamps for each of the nodes where they are created and when they are deleted. And this is actually something that turned out to be quite tricky to define because the graph has a lot of implicit rules that in practice are enforced by how just the word works and how the users behave. We had to incorporate them in the generator. What I mean by this is that if you are a person and you would like to post a message to a forum, in real life, you have to first become a member of the forum, and only then you can write that message. The way our generator implements this is that it sees the entire temporal graph as one with all the creation dates and all the deletion dates back in the past and forward in the future. So if a person wants to create a post in the message, it first has to become a member. To achieve this, we first select the interval that captures the valid potential time interval for becoming a member. Obviously, if the person wants to become a member of the forum, both the person and the forum have to exist during this time. Then we select a time on this interval and say it has to be deleted sometime. So that is sometime after it has been created, but before the forum is deleted. We then select the deletion date and designate this as the lifespan of the member edge. Once the person is a member, we can create a post during any time point of this membership. We just select the creation date, say that it also has to be deleted at the very latest with the membership, and then we get the post, which is going to be the lifespan of this post. So you can see that there are kind of lots of constraints, and if you want to build a thread of messages, it's actually quite constrained in time. Obviously, we have 3 years to do it in the simulated time of the generator, so there is enough space to do this. Once we have done that, we actually feed through the temporal graph on 2 components. One creates an initial snapshot which simulates the data dump. It's roughly 97% of the entire graph. And we take the rest, which is a 35-day period, and split it into daily batches, each containing insert and delete operations. And these are then executed throughout the benchmark. One unique feature of our benchmark compared to the analytical TPC benchmarks is that deleting entities are heavy hitting operations. It's not just deleting one row or maybe a couple other rows which are connected through a foreign key. This can affect a few hundred or even a few thousand nodes. For example, in this toy example, we can see that deleting a forum removes most of this graph in form of the message thread in the middle and all the edges that the forum or any of the messages have with adjacent nodes. If we delete a person, it can easily delete 5,000 to 10,000 entities in the graph. Okay, so how does the workload of LDBC look like? When designing our workload, we followed a choke point based approach. This is based on the TPC-TC 2012 paper by Thomas, Peter, and Ori Erling, where they analyzed TPCH on 3 state-of-the-art analytical database systems. We took their output and extended it with graph-specific operators, for example, worst-case optimal joins or path queries, and tried to design queries so that these choke points are adequately covered and the systems which work on these choke points, for example, systems which implement worst-case optimal multi-way joins, benefit from being faster on those operations. The workload looks as follows. We have ad hoc graph OLAP queries, meaning that they have to be formulated in some sort of domain-specific language, because that's a realistic scenario for data scientists to use. We have batches of write and read operations. We first load the initial bulk set of the data, then do a power test, which is a sequential execution of the reads. And then for the rest of the time, we simulate as if this system would do a daily analytical cycle where the updates are loaded and the queries are executed. We have 20 complex read queries with different parameters. We'll talk about that in a moment. So I mentioned that we have this unique technique called parameter curation. It turns out that parameter selection is particularly important for skewed and correlated data sets. And what we mean by this is that such an innocuous query which says start from person 1 and then find friends and friends of friends who created messages in a given range constraint can be very different in terms of execution. Imagine that you run this query on someone like Justin Bieber on Twitter who has 100 million followers, or you run it on a person who just joined the network and maybe doesn't even have any connections. It can be like dozens of orders of magnitude in difference. And obviously we don't want that. We want predictable, scalable, predictable and stable runtimes to make the results easy to understand. Another interesting variant of this problem is reachability queries. It turns out that if there is a path in a social network, it's usually very easy to find. You can do 2 or 3 hops and there is likely a path between 2 randomly selected people. But if there is no path, one has to traverse the entire connected component of one person to prove that such path doesn't exist. And that's, again, a very different query, and it gives very different runtime characteristics. Here's an illustration of what we mean by this. These results were achieved on the LDBC BI queries with the Umbra system using parameters that we just selected with a uniform random sampling and parameters which we then created with curation. What one can see is that the purple ones with naive parameter selection always have very heavy outliers. It's usually a bimodal distribution or a multimodal distribution. And this is precisely because we happen to involve heavy hitter nodes, ones with a large out degree, or in the case of 3D20, we select cases when there is a path, which is very easy for the database to find, or cases where there is no path, which then takes more than 100 times longer. So parameter curation is our technique to prevent this by selecting parameters that result in similar runtimes. A couple of the queries that I would like to highlight are the graphy ones that really do something that is unique to graph databases or graph data management in particular. Query 11 is a triangle query which looks for people who live in the same country and form a triangle of friendship. And we can see that parameter curation here is again very important, because if we randomly select countries, we will hit many small countries or just one big country, which will produce an outlier. So yeah, to redeem this, we only select big countries and similar time intervals for the triangle of friendships to form. Another interesting query is one which finds people who live in adjacent countries or live in country 1 and country 2 and know each other. And it turns out that if we select people who live in faraway countries and versus close countries, we will get wildly different query runtime results. Of course, people in adjacent countries tend to know each other better and tend to form more connections and more interactions through messages. A couple of the path queries that we find important are the weighted shortest path, also known as cheapest path queries. This query takes 2 cities and tries to find the shortest interaction path between its citizens. Again, it is really important to select cities of similar sizes because it really influences the query result. But we have 2 variants. In variant A, we do cities from the same country. Again, there's likely a short path and there are likely many paths between 2 people. And with B, we select people from different countries. And finally, we have this recruitment query where we say we want to recruit person 2 to our company. And our way of doing so is to compute edges where the weight is determined by the enrollment of class year of the 2 people to the same university. And we expect the 2 people to go to the same university. And one would expect that this graph is pretty sparse for if we would generate it with some uniform random approach. But because being enrolled in the same university is actually one of the indications of becoming friends in real life and also in our data generator, it is actually quite a dense graph, and this is a pretty heavy query for systems to solve. To ensure that we have predictable runtimes, we have designed the parameter generator in a way where variant A ensures that there is a path between the company employees and the selected person 2. And in variant B, we guarantee that there is no path between the company and person 2. So one of our goals with this benchmark is, of course, that it should be implementable, it should be portable, and it should be doable with a relatively reasonable amount of effort. To prove this, we have 3 reference implementations with Neo4j, a graph database, Umbra, a relational database, and TigerGraph, a graph database. One can see that all systems managed to implement this benchmark between 500 and 800 lines of code. So it's definitely something that experts can implement in a matter of few weeks. Okay, onto the execution, auditing, and scoring rules. So I mentioned that we have a power test with sequential query execution, and we also have a throughput test where concurrent query execution is desirable because that's how systems can get the most throughput. However, we made a deviation from how TPC approaches things. Namely, we say that it's possible to run overlapping writes and reads in the throughput test. But if a system chooses to do differently, they can do a similar run to the power test when they first apply the writes, and then they apply the reads, maybe concurrently, maybe sequentially. The rationale for this is to allow systems such as Spark to compete, because vanilla Spark is really not great at doing concurrent reads and writes, but we can imagine that it would play the role of the analytical system of our example data pipeline. So this is something that we have considered, and we also made this choice so that the barrier of entry is a bit lower to this benchmark. So we run these benchmarks and collect all the execution times during the phases that the system goes through. We then derive two metrics for scoring. One is the power metric, which is determined as the geometric mean of the write time and the 28 query variance. Then this is of course scaled up by the scale factor similarly to the TPC. We selected geometric mean to ensure that all queries are of equal importance, and it's not just the long-running queries that deserve the attention of the vendors. Next, we do the throughput metric calculation. To this, we run the throughput tests, and when at least 1 hour has passed, we cut it and say we have run n batches during this time, and we extrapolate it to 1 day. The idea is that this is a metric that tells you how many batches could this system sustain throughout a continuous execution in 1 day of execution time. Again, we slightly deviated from TPC-DS and the other TPC benchmarks because we not only report the load time in our disclosure reports, but we also include the load time in this result. So from the 1 day, we have to deduct the load time first. This scoring metric, of course, implies two things. One is that the loading time has to be less than a day, which we think is a realistic expectation. And the other is that the system has to complete at least 1 batch in the remaining period of a day, which again is pretty realistic if you would like to do data analytics with a daily batch. Once these metrics are calculated, we create price performance metrics. We do this by multiplying them by 1,000 and dividing them by the total cost of ownership. The total cost of ownership includes the software licensing cost, software maintenance cost, and also the cloud costs. Traditionally, this used to be hardware cost, but we have seen that vendors very quickly moved towards focusing on the cloud. So we have established the cloud cost to be a 3-year reserved instance, and the required extra costs to be included in the total cost of ownership. So to sum up, we believe LDBC SNB is a state-of-the-art analytical benchmark. It already scales up to 10K scale factor graphs. This means it's roughly 10 terabyte in uncompressed CSV sizes. To put this into perspective, in the last 10 years, TPC age benchmarks were also in a similar ballpark, except for 14% of their benchmarks, which used scale factor 30K or scale factor 100K. We believe our generator is capable of doing that, and it generates more sophisticated graphs, but there is some more engineering to be done. As Peter said, we have written this up into an experiments paper and submitted it. Hopefully, it will be circulated among you soon. As to our next plans, we, of course, are very interested to start audits with this new benchmark, go to larger scale factors, and then backport the improvements, including the inclusion of deletions and also the larger scale factors to the SNB interactive framework. Thanks, and I'm happy to take any questions.
Thank you, Gábor, for your presentation. Can you elaborate more on the temporal data model. Does it mean that in the query you can include predicates on the timestamps? Can you, because in your example, it was not entirely clear.
Thanks. So the question is including predicates on timestamps. This is definitely possible and exploited. So all the dynamic part of the graph comes with an attribute called creation date, which designates when that particular node or edge is inserted in the graph. And we make use of this in the queries. Another aspect of looking at this is to tell the data generator to stop at the generation of the temporal graph and do not split it into daily batches, just create something that we call the row graph, which has all the creation dates and the deletion dates. And this can be used for things like temporal analytics. You can replay the entire graph with the granularity of a millisecond. So that's also something that we hope the streaming community will pick up, because we don't really see any other alternative graph generators.